Welcome to CBSEasy.
All right, everyone. Today we're tackling one of the most important chapters for your board exams, electricity. We're going to cover everything from the basic laws to solving some pretty complex circuits, giving you all the tools you need to really nail this topic. Okay, let's just dive right in. We're going to start with a challenge, a real question from a sample exam paper. Now, I know it might look a little intimidating with all those wires and resistors, but I promise by the end of this, you'll see exactly how simple it can be. So here's our game plan. We're going to build up our skills step by step. We'll start with the fundamentals, Ohm's law. Then we'll get into series and parallel circuits, and then we're coming right back to solve this exact problem. And finally, we'll talk about why this all matters in the real world. Let's get started with our most important tool, the one law that pretty much governs everything we're going to do today. It's the golden rule of circuits. In simple terms, this amazing law, figured out by George Simon Ohm, gives us the core relationship between three key players. You've got voltage, which you can think of as the push. Then you have current, which is the flow. And finally, resistance, which is basically the opposition to that flow. Now, what's really cool about Ohm's law is how versatile it is. See, these aren't three different formulas. They're just three different ways of writing the exact same rule. It means if you know any two of these values, like voltage and resistance, you can always find the third. And this graph, this just illustrates the law perfectly. If you plot the voltage you apply against the current that flows, what do you get? A perfect straight line. If you double the push, you double the flow. It's just that clean and simple. Think of resistance as a kind of electrical friction. It's what slows down the current. And here's the thing. Every single component in a circuit, from a tiny wire to a giant light bulb, has some amount of resistance. Okay, so now that we've got our basic tools, Ohm's law and the idea of resistance, let's see how they work in the two main ways you can actually build a circuit, connecting things in series or in parallel. Now, this slide is absolutely crucial. Understanding these differences is the key to knowing which formula to use. Think of a series circuit like a one-lane road. The current only has one way to go, but a parallel circuit, that's like a highway with multiple lanes, so the current splits up. Getting this down is everything. Okay, listen up, because this is a super common mistake. When you're dealing with parallel circuits, you calculate 1 over the total resistance, which gives you a fraction. You absolutely must remember that final step to flip the fraction over to get the real answer. Seriously, don't fall into that trap. For series circuits, things are beautifully straightforward. To get the total resistance, you just add up all the individual resistances. It's as easy as that. The more you add, the higher the total resistance gets. And for parallel circuits, you add the reciprocals. Now, here's a cool little fact. This means the total resistance in a parallel circuit is always going to be smaller than your smallest individual resistor. Why? Well, you're giving the current more paths to take, so the overall opposition to the flow actually goes down. All right, it's time. Let's go back to that challenge problem from the beginning. Now that we know about Ohm's law and the difference between series and parallel, this diagram that looks so complicated is about to get a whole lot simpler. So let's look at it again. What do we have here? We've got a 6-volt battery that's giving us the juice. We have two 24-ohm resistors hooked up in parallel. And then that whole parallel section is connected in series with another 12-ohm resistor. Let's break it down. First things first, you always want to simplify the most complicated part first. And that's usually the parallel section. Our goal is to replace those two 24-ohm resistors with just one single resistor that does the same job. So we'll use our parallel formula. So let's do the math. 1 over 24 plus 1 over 24 gives us 2 over 24, and we can simplify that to 1 over 12. But wait, we're not done, right? We have to remember our rule. We flip it, and the equivalent resistance is 12 ohms. Perfect. Now the circuit is so much easier to look at. In our heads, we just have our new 12-ohm piece, and it's in series, in a straight line, with that other 12-ohm resistor. To find the total resistance for the whole thing, we just add them up. And the math is as simple as it gets. 12 plus 12 gives us 24 ohms. And that's it. That is the total overall resistance of the entire circuit. We've managed to boil that whole messy diagram down to just one number. And for the final step, we get to bring back our hero, Ohm's law. We know the total voltage from the battery, and we just figured out the total resistance of the circuit. That's all we need to find the total current flowing out of the battery, which is exactly what that ammeter is there to measure. So with our 6-volt battery and 24 ohms of total resistance, the current is just 6 divided by 24, which is 0.25 amps. And just like that, the problem is solved. That intimidating circuit is cracked. See? Not so bad, right? Okay, so let's move to our final section. We've totally mastered the math, but so what? Why does this stuff actually matter? Let's look at the real-world consequences of all this electricity flowing around, specifically how it generates power and, of course, heat. This is the reason why your phone charger gets warm when you use it, or why an electric stove gets red hot. That resistance we've been talking about actually causes some of the electrical energy to turn directly into heat. And Joule's law here tells us exactly how to calculate how much heat we're going to get. Now, this heating effect isn't just some random byproduct, it's incredibly useful. We actually harness it on purpose in all sorts of devices, like electric heaters and irons. It's also the simple but brilliant idea behind a fuse, which just melts and breaks a circuit if things get too hot. And of course, it's what makes the filament in a light bulb glow. So, to wrap everything up, here they are, the essential formulas you need to master this chapter. Seriously, think of this as your electricity toolkit. With these 5 equations, you can analyze pretty much any circuit, calculate power, and understand the core principles of electricity. Keep this handy and you'll be all set to solve any problem that comes your way.
Thank you for watching with us. See you next time.